our liquid phase and our gas phase chemical potential curves. And again, the gas phase is going to stay constant. The chemical potential of the liquid phase is going to drop. This is for non-volatile solute. And the point of intersection of the two curves changes and shifts to a higher temperature. And so the suggestion is that the lowering of the chemical potential of the solvent by dissolving the solute into it has shifted the boiling point temperature to a higher temperature. Let's look back at this diagram. So I should have mentioned that these are defined for non-volatile solutes. We're kind of exploring non-volatile solutes right now. The boiling point is defined to be the pressure, the internal pressure at which the temperature at which the vapor pressure of the species is larger than the atmospheric pressure, right? So if the vapor pressure is pushing on the atmosphere with some pressure that's larger than the pressure that the atmosphere is pushing back on, you'll get spontaneous movement from the liquid phase into the gas phase, right? We talked about that. You dissolve a solute into this, and all of a sudden, some amount of surface area that was previously available in the pure solution, or in the pure solvent, is occupied by these solute species. And so you don't have, at a given temperature, constant temperature, you don't have as much transfer from the liquid state into the gas state, because there isn't as much area available for these things to depart from. And so to reach a vapor pressure at which your vapor pressure is larger than atmospheric pressure, you're going to have to increase the kick that you're pushing these guys out with. You're going to do that by increasing the temperature. And so if you dissolve a solute into a substance, you raise the temperature at which the vapor pressure of the substance is equal to the atmospheric pressure. Therefore, you raise the boiling point. So dissolving a solute species into a solvent raises the boiling point of that species. It lowers the freezing point. These are boiling point elevations and freezing point depressions. We're not going to do the derivation for the boiling point elevation and the freezing point depression. I might do it next week, or maybe not next week. I got all that stuff to cover. But you can look at the derivation in your book. When you express this mathematically, you find that the change in the boiling point of the freezing point is proportional to RT squared over the delta H of the transition, whether that's fusion or vaporization, times the mole fraction of the solute. And so this factor of the mole fraction of the solute basically says that the more species you have dissolved, the larger the temperature change is going to be, which kind of fits our model. We looked at the freezing point depression and the boiling point elevation as a function of having interference from the solute species in the phase transition, and so you would expect that the larger the number of these species you have, the greater the magnitude of the effect is going to be. All right, one last subject to cover, and that is osmosis. And for osmosis, you guys, a lot of you are in labs, you probably use osmosis. You you have a situation where if you take a solution of some species and you put them, you separate it from a pure solvent via a porous membrane. If this membrane is not permeable to the solute species, but it is permeable to the solvent, what you'll get is a net transfer of solvent into the solute. Solvent will evaporate. And what will happen is that the volume of this compartment will decrease and the pressure in this compartment increases. There's a reason for that, and it goes back to equilibrium. So we know that at an equilibrium condition, the chemical potentials of all the species are equal, right? And what we have here in the situation where solvent is allowed to flow but solute isn't, is we have a question of what is the chemical potential of the pure relative to the chemical potential of the solution. At equilibrium, they have to be equal, right? Once this thing stops moving, once all the water that wants to move over to this side has moved over, and you've reached some equilibrium condition, the chemical potentials of the solvent over here in the pure is equal to the chemical potential of the solvent in the solution. We just said that adding a solute to this solution decreases the chemical potential of the solvent, right? Goes as RT, natural log of the mole fraction. And so by adding this solute to this solution, we've decreased the mu of the solvent over here in this compartment relative to the mu of the pure. Yeah? At equilibrium, they're equal though. So if we've decreased the chemical potential by adding solute, but ultimately at the end of the process, the chemical potentials end up equal, we must have increased it some other way in a fashion that was equal and opposite to the magnitude that we decreased it by adding it, right, making it go in the solution. You guys saw that dG is equal to negative S dt plus V dP. Constant temperature, we don't have to worry about this. But this equation tells us that the chemical potential of a species increases with an increased pressure. What happens in osmosis is that the solvent will move over into this other compartment, increasing the pressure in that compartment. When the pressure in that compartment increases, the chemical potential of the species increases. So in osmosis, we have an equalizing effect where the pressure increases just enough to overcome the lowering of the chemical potential due to the addition of the solvent, the solute. Let's look at the way this looks mathematically. So I've broken this apart into two steps. One is what is the delta G of the pressure. One, what is the delta G of adding the thing into solution. So we said that the delta G for adding it into solution is RT natural log of XA. Delta G due to an increase in pressure is the molar volume times the change in pressure. We're going to define delta P to be equal to this thing pi called the osmotic pressure. And so we end up with the relationship that molar volume times pi is equal to negative RT natural log of the mole fraction of the solvent species. XA is equal to 1 minus XB, and the natural log of 1 minus XB, where XB is much smaller than 1, is approximately negative X. And so we end up with this equation that says RT XB is equal to the molar volume times the osmotic pressure. And that is the equation that you start at for the osmotic pressure for this process. There's a couple of other manipulations that recast it into a form that your book tells you to use, but this is the starting place for quantifying the osmotic pressure. You can think of the osmotic pressure in a way similar to the way that we looked at the boiling point elevation and freezing point depression. At this membrane boundary, you have water molecules on one side, or solvent molecules on one side trying to cross the membrane and go to the other side, and you have molecules on the other side trying to cross and move over here. At equilibrium, the flows are identical. But on this side, you have solute molecules kind of occupying the surface area of the boundary. And so there's not as much room for solvent to cross from this side to this side as there is for solvent to cross from this side to this side. And so if the rate of flow is going to be identical, then the force with which water molecules or solvent molecules are hitting that membrane from this side has to be greater than the force that they're striking it from the other side. And so an increase in pressure over in this compartment increases the force with which these solvent molecules are pushed towards the other side. It's got to be increased because, like we said, now we've got all these little solute particles that are standing in the way and not allowing transfer to happen. What's reverse osmosis? Reverse osmosis is a technique for separating solvent from solute. You simply increase the pressure so that it's greater than the osmotic pressure, and now you'll get net transfer over to the other side. Use that for desal and other things. All right, that's it.